Welcome to the AICE Math Review on Integrals. This is going to be one of the last few videos of the series. I want to make this introduction to integrals one video. I know that the derivative introduction spanned 3 videos and that was a lot. So I'm going to keep this pretty short and use one example from each of the integration formulas that we're going to use that I'm going to write down actually on here. So our first one is x to the n, and the integral of that, we're just going to add 1 to the exponent and divide by that new number. And I'll explain the plus c and all that. So yeah, this is just going to be one video. It'll be kind of a little longer, but we'll see. We'll see how it goes. Okay, so we're going to talk about 2 different types of integrals, definite integrals and indefinite integrals. This is an indefinite integral. If it had numbers here, it would have been a definite integral, and I'll go over that in a second. But basically, what we're going to do is we're going to add 1 to each of these exponents. So 1, integral of 1, you can think of this as the integral of 1 times x to the 0, okay? And so if we add 1 to that exponent, this will turn into x to the 1 divided by 1, or just x, okay? So that's going to turn into x, and then we're going to add, so then we have this 2, we leave the 2, we add 1 to the exponent, this is going to turn into x squared divided by 2, plus this 3, this we add 1, 2 plus 1 is 3, so this is x cubed divided by 3, then we just do the same thing here, x to the 4th over 4. And we can kind of just cancel out all of these 3's and 4's because, you know, this technically is just a 1x over 1, so we can cancel those out. So this actually turns into a nice equation, which is just x plus x squared plus x cubed plus x to the 4th, okay? Now we have to add a constant because the integral, basically all it describes is the area under a curve of a function, which the area under this function would be this function. Now if we plug in numbers, we'll be able to find ranges, and I'll explain what that means in a second. But basically, you have to think of derivatives and integrals as inverses, because that's what they are, okay? If I took the derivative of this, I would end up with this. Now, if there was a number here, like 70 or 10 or 2.5, the derivative of a number is 0, so it would kind of just go away. So if we're doing the opposite, we have to add a constant because we don't know if there is a number there. So that's why. So we add a number there. So I was mentioning indefinite integrals and definite integrals. So a definite integral would have a number here. So let's say our numbers were 0 and 3. So we're finding the range of the area of the function from those 2 values. So let me just draw a picture to kind of explain this to you. So let me draw it over here. So we have this function, let's just say this is from 0 to like some number, it doesn't really matter. And so let's say this is our function. I'm not saying this is exact, but let's say our function looks something like that. If we're going from 0 to 3, let's say 3 is here, we're trying to find the area here. That's the area we're trying to find. So that's what we're doing. So let's say we have from 0 to 3, so we plug in, so let me just draw like this this kind of box, I guess you could think of. So from 0 to 3, a lot of people just do like a horizontal line here, but you know, whatever you want. So from 0 to 3, we're evaluating this. So we plug in 3 for all of these, and we subtract 0. So let me kind of just do this here. So we're starting with our 3, so we have 3, plus 3 squared plus 3 cubed plus 3 to the 4th. Okay, now the c, we kind of don't really worry about it because it's kind of just there, so I'll kind of show you what I mean here. So we have this plus c, okay, and then we're going to, whoa, that's it's a little thick for what we need here. There we go. Okay, and then we're going to subtract what we have here. So we have 0 plus 0 squared, and you can kind of see this is just going to be 0. But then we have this plus c at the end. Okay, so what we do is, since this is just 0, we can kind of just leave it alone. So we just add up all these values. This is going to be 3 plus, so let me do it in black. So we have 3 plus 9 plus 27 plus 81. Okay, so this plus c, we're going to subtract another c, so it kind of just goes away. And you can think of it as, well, we know the range. We know the range of values, so we don't need a constant, because we're going to get an answer anyway. This is good. This is a number, you know. The equation just tells us the equation of the area. This number is going to tell us the exact area from these two values, because you're going to get a number if you know your range. So let's just add these up. This is going to be 90 plus 30, and that's going to be 120. And that is our area. So that's our first integral. Now, if you notice, your n, if it's -1, you add -1 plus 1, that's going to be 0. And if you have to divide by 0, you end up with a problem. So what happens if your n is -1? Well, there is actually an equation for that. There is a defined function for your integral, so we're going to go over that next. So now I'm going to introduce some new ideas here. So I have this crazy expression, and we're going to try to find its integral. So the first thing you can think of is you can actually just separate each of these terms into their own respective integrals, because I mean, you're doing each term individually, so you can actually just break it up. So let's do that for simplicity. And since you're multiplying by a constant, you can actually factor that out of the integral symbol, because it doesn't depend. Like, whenever you have a number there, you're just multiplying. It doesn't depend on any function you're working with, and so you can kind of just put it outside of the integral. So let me break it up and do all the steps I have. So 5 times the integral of 1 over root x. And let's actually, we can take it a step further and actually just rewrite this. So this is just x to the -1/2, right? Because we have it on the bottom and it's a square root, so x to the -1/2 dx plus, well, we can factor the 6 out, and then we have 1 over x there, so we can leave it. We don't have to do x to the -1, so it's 1 over x dx. That's going to be a pretty easy one to do. And then we have this 7 times the integral of 1 over x minus 1 dx. And we'll worry about that in a second. But for now, we can just do this. This is what we have been doing. We add 1. So it's going to be 5 times x to the 1/2 divided by 1/2. Okay. So let me just do an equal sign here. And we can actually kind of already simplify this. This is dividing by 1/2 is the same as multiplying by 2, so we have this 10 times root x. Okay, here we are going to add, I'll just do another equal sign here. So we have this 6 times 1 over x. Integral of that is a natural log of the absolute value of x. Keep in mind that there has to be an absolute value, because natural log is not defined for negative values. It's only, I mean, unless you're in the complex world, but for real values, the natural log is only positive. So that's why it's an absolute value. So natural log of x, okay? Yeah, so I'm going to just do each of these individually. So this is just 6 natural log of x, okay? And I guess you add the plus c, I'll do a plus c1 and a plus c2 here, okay? And I'll worry about those in a second. Now, we have this x minus 1. We don't have a product rule or a quotient rule or a chain rule in integration, so what we do is what we call u substitution, where we substitute u for a value of a function of x, basically. So let's say our u is equal to x minus 1. Okay, so now we have this 1 over u. So we can actually just do this equals 7 times, actually let me give some space here. So 7 times 1 over u, okay. So we can't have a dx, because the dx tells us we're taking the integral with respect to x, and we're not using x, we're using u. So we need to find our du, which we can do fairly easily. And you can, once you do this, after you do it a few times, you can kind of just skip steps. So we'll say the derivative of u with respect to x is equal to x, derivative that is 1, derivative of the negative 1 is 0, so it's just 1. So then we can multiply both sides by dx, and we're left with du is equal to dx. And yeah, so then we can kind of just add this du and multiply by 1, because du is 1 dx. So yeah, I mean, we'll come up with more difficult problems in a second, but for now this is fairly easy. So then we have this, we have 7 times the natural log of u. Okay, and then we're going to add our third constant. Okay, but we can't use u, we have to substitute everything back. So we have this x minus 1, so really this is just 7 times natural log of x minus 1. I don't want the 1 to look like a absolute value bar, plus our same constant. Okay, so our entire answer, since we had one integral, our entire answer is going to be a combination of all of these. So our final answer, I'm going to worry about the constants in a second, so just don't worry about it for now. We have 10 root x plus 6 natural log of absolute value of x plus 7 times natural log of absolute value of x minus 1. Okay, now we have 3 different constants here. It doesn't matter, because we should end up with one constant at the end, because we could have just done this without splitting it up. It's just more easy to split it up, and so you would have ended up with you would have ended up with one constant anyway. So you're adding 3 different numbers, you're going to get another number. So we can just say this is plus our final c, and that is our answer. So yeah, I mean, this does take a while in the beginning, but u substitution can be quicker after you do it a while. You don't have to worry about the du dx, you can kind of just do du dx, and we'll go through that in a second. I'm going to do one more example with u substitution, since it's important, because you're going to have to use u substitution in a lot of integration, so it's really important to go over it. So here, we can notice that I can actually just move this 3, I can actually just move it on the outside here. Okay, that just kind of makes our lives a little easier. Okay, so what I can also do is make a substitution that 6x plus 5 is u, because then we can easily use our power rule right there. So u is equal to 6x plus 5, okay, and then our du, see, I'm skipping the du dx step because I know I'm going to multiply by dx anyway, so it's just going to be 6 times dx, because the derivative of that is 6, okay, and so then I can actually just move this 6 over, because we want to find what our dx is, and so if we know what 6 dx is, we just have to divide by 6, so then we get 1/6 du is equal to dx, okay. So now we have our du expression in terms of dx, or the other way around, so then we can actually just substitute all of this back in. So we have this 3 times the integral of u to the fourth. So we have u to the fourth. I put too much effort into these. And then we actually multiply it by 1/6 du. So the 1/6 can actually just go on the outside. And then we have this du. Okay? I don't know why that u is so bold. But yeah, so we can actually just take the integral now. So 3 divided by 6 is just a half. We can worry about that right now. 1/2 times our integral is going to be u, which we can actually just make the substitution back already. So 6x plus 5 to the 5th power divided by 5. And then we're going to add a constant. And that's it. I mean, we can say, all right, well, let's multiply that by 1/2, and that's going to turn into 10. And that's our final answer. And so let's say we had a definite integral from, I don't know, 0 to 1, just to make easy numbers here. So this, we're going to get rid of the c because we don't need it anymore. We're going to evaluate this. I'll just do the bar notation just so you can be familiar with it. So we're going to do this from 0 to 1. Okay, so this is going to give us, we have this 6 times 1 is 6 plus 5 is 11. 11 to the 5th. I didn't know what I was getting into whenever I was like, oh, I'll just plug in 0 and 1. They're small numbers. It's fine. Didn't realize it was actually going to be a crazy answer, but don't expect crazy answers like 11 to the 5th. You're never going to need to do that on the AICE exam. Actually, I don't know. You might, but I mean, you have a calculator, so if you have to, then you can. So yeah, you end up with 15,792.6 as the answer from 0 to 1. If it was just a general, you'd end up with that. So yeah. Now sometimes whenever you're dealing with integrals, you have other variables, such as whenever you're working with time, usually t is your variable. And so sometimes you're going to need to do stuff with dt. It's the same thing, you're just using a different variable. So we're introducing exponentials, where derivative of integral of e to the x is e to the x, because the derivative is e to the x. So yeah, it's actually a very interesting thing. But yeah, so this, we could do a u substitution that e to the 2t plus 2 is our u, but that's kind of complicated. The best thing we can do is to just FOIL it out. So yeah, let me just do this. So we have e to the 4t, because we're going to multiply that squared, plus 2e to the 2t, no, 4e to the 2t, because we're doing that, 4e to the 2t plus 4 dt. Okay, so now we just FOIL it out. We actually need to do a substitution here. We need to do two substitutions because we have the 4t and the 2t. So let's keep it in one integral so that it goes by pretty quickly, or a lot quicker than having to split it up and then do that. So we're going to do u is equal to 4t, so then du is equal to 4 dt, so we can just do 1/4 du is equal to dt. And then for this 2t, I don't want to use u again because that would be very, it would be kind of confusing, so we're going to do another substitution. We'll do w. W sometimes is good. So w equals 2t, and then 1/2 dw is equal to dt. And then the 4, we don't have to do any substitutions. Okay, so actually we do have to split it up because we have these variables and it's going to be kind of crazy. So we have 1/4, yeah, let me do it in this color. So we have 1/4, okay, times e to the u du, okay, and then we're going to add that to I'm going to do 4 times, because we have that 4 there, times 1/2. Okay, and then we're going to multiply, or yeah, it is multiplying, by e to the u du. No, this is supposed to be red. Why? Okay. I'm not doing it that boldly. Alright, e to the u du. That looks like a v. I cannot write today. Alright, and then we have we can actually just do this pretty easily. That's just going to be 4t. Okay, so we can do these substitutions now. We have this 1/4 times e to the u, which is 4t, so e to the 4t. I'm going to hold off on adding my c again for the same reason as last time, and then we have this 2 times e to the, actually this is a w. See, you can't mix things up, and I just did, so I apologize, but yeah. So w is 2t, so this is just e to the 2t. Okay, and then we again have our 4t, and plus c. Okay, so that's our equation. We can't really simplify it much unless we factor things out, but that's not really necessary for our purposes. So yeah, that is our equation. So now I want to introduce the sine and cosine integrals. Sine turns into negative cosine, and cosine turns into positive sine. So basically inverses of the derivatives. Derivative of cosine is negative sine, derivative of negative sine is positive cosine. So, or no, derivative of positive sine is positive cosine, yeah. So, okay, again, we should do a u substitution, and I left a space here on purpose because what we can do is turn this into a sine of 1/2 t, or just sine of t times 1/2, okay? So that is going to help us with our substitutions. So let's do our substitution. So again, we're going to have to use 2 different variables. Let me just get rid of that there. We're going to have to use 2 different variables, and that way we can distinguish between these two. So we're going to do, we can use a and b. Actually, let's just use u and w like we did last time. So if we set u equal to 1/2 t, okay, then our du is just going to be 2 du is equal to dt, okay? And if our w is 2t, then our dw, so we have 1/2 dw equals dt. Okay, so that allows us to split, or not split these up, but substitute things in. So now we can actually split them up. So we have the integral from pi over 2 to pi of sine of u times 2. So we can put this with 2. Okay, sometimes it's bold, sometimes it just doesn't feel like writing. So we have sine. Okay, same thing with this. Let's try and have to like angle them in a specific way. Sine of u du. Okay, and then plus, again, since we're using different variables, we have to use 1/2. So yeah, I'll do that in red. So 1/2 times our integral from pi to pi over 2. Switching colors is a little, it's useful, but it's hard sometimes. 1/2 times our cosine, or cosine function, cosine of w, not u, w dw. Okay, and so this should be our integral. Yeah, it is. So now we just evaluate it. So first we have to actually find it. So 2 times, I'm going to put the brackets there right now so that we can get ready. So sine x turns into negative cosine. I'll put the negative to the front because you can do that since it doesn't depend on anything, you're just multiplying by a number, so you can put that out to the front. So then we have this cosine And before you plug in these, you have to put your u back in. So we have this cosine of 1/2 t, okay? Yeah, and I'll close that there. And we go from pi, we do it in red. So we go from pi over 2 to pi over 1. And then we have this 1/2 times this box thing. Cosine turns into positive sign, so we don't have to use a negative. Sine of w is 2t, so sine of 2t from pi over 2 to pi. Okay, so again, we have to evaluate each one individually. So we have -2 times cosine of, so it would be pi over 2, so if t is pi, so then it's just going to be pi over 2, so cosine of pi over 2 minus cosine of, so this is going to be pi over 4 plus 1/2 times sine of 2 pi minus sine of 2 times pi over 2 is just going to be sine of pi. Okay, so we can actually, for these three, we can use just drawing our sine graphs. So let me do that in red here. So if we draw our sine and cosine graphs, we have 2 pi, pi, and then we have our 4. This is pi over 2 right here. So we need pi over 2, we need pi, we need 2 pi. Okay, so our sine looks like that. Okay, that should be right there. Okay, and our cosine looks like that. So this is sine, and this is cos. And I'll put the x there. Okay. Okay. So we have this -2 times cosine of pi over 2 is 0. So this is actually just very easy 0. And then cosine of pi over 4, which we need to figure out, we can actually use a sine and cosine chart. So sine and cos, and I'll just put the x there. So 30 degrees, we need 30, 45, and 60, which is just pi over 6, pi over 4, and pi over 3. This is something you should definitely know. If you don't know, you should definitely learn about it, but you should know that these are 1/2 square root of 2 over 2 and square root of 3 over 2. And the cosine is the reverse, square root of 3 over 2, square root of 2 over 2, and then 1 over 2. Or you could think of it as square root of 1 over 2, okay? So what we need is pi over 4, and we need the cosine, which we just matched up, and we get this square root of 2 over 2. So I'll just do that in black. Square root of 2 over 2 plus 1/2 times sine of 2 pi is 0, and sine of pi is also 0. So this is just 0 minus 0. Okay. And this becomes, our final answer is going to be -2 times root 2 over 2, which is going to be positive square root of 2, plus 1/2 times 0 is just 0. So this is our answer, square root of 2. I forgot to put the number 5 there earlier, so I hope that didn't bother you, but now we're doing number 6. We are using thetas, because you can also come across thetas. So tan squared theta, d theta. You can think of them as just x or t or anything. So yeah, we actually don't know what the integral of tangent squared theta is. We know that like the integral of secant squared is tangent of x plus c, but we don't know what tangent squared is. So let's just think of some trig identities. So we know that sine squared and cosine squared make up 1. So we can use that fact. Okay, so sine squared, I'll use x, because why not? Cosine squared x equals 1. If we divide all of those, so we just divide by cosine, cosine squared. So we're going to divide each term by cosine squared. We end up with tangent squared plus cosine divided by cosine, or cos squared divided by cos squared is 1. That's equal to 1 over cosine squared x, which is secant squared x. See where I'm going? So now, if you want to equate this to tangent squared, you just subtract 1. So this is just minus 1. That's it. Tangent squared of theta is equal to secant squared of theta minus 1. So we can make this pretty easy substitution. So we have this thing, the integral symbol there. So we get secant squared theta. Actually, I like to do my thetas like that, but it's best if it's like that. Minus 1. And we are doing d theta. Man, I need to learn how to use markers. D theta. Okay. So, we know that the integral of secant squared is tangent, so we can make this, it's actually a pretty easy one. This is tangent of x plus, or minus actually, because we're subtracting 1, x, because integral of 1 is x, or no, it's theta. See, you gotta make sure you're using the right variable, and then we're adding a c, and that's our answer. Tangent theta minus theta plus c. That's the answer to tangent squared theta d theta. So yeah, that's pretty much everything about integrals that you should know for now, until the integral applications come around. And so, but other than that, these are just the basic integrals covered in 6 problems. So hopefully that helps you. But yeah, thanks for watching, and I will see you all in the next episode. Bye.